Hello, AP Stats. Today we're going to talk about section 6.3, probability distributions for continuous random variables. This section's pretty easy, pretty simple, should go pretty quickly, but it's going to lay the foundation for our normal distributions, which is huge for us. If at any time you feel like I'm going too fast, just pause and jot yourself down some notes, follow from there. Okay. A probability distribution for a continuous random variable doesn't come from a table. We saw that our tables are used for our discrete functions where you have your x and your probability of x. The distribution for a random variable that is continuous comes from a function. That function is known as f of x, and we call that our density function or our density curve. And the reason we call it the density is we end up using the area under the curve. Now, all of you people in calculus, don't worry, we're not going to be doing any integration because the only requirement to be in this class is Algebra 2, so you don't have to worry about that. Our density or our area under the curve is going to be really easily calculated through our calculator or tables or whatever else we need. These continuous probability distributions are kind of shown in two ways. You have your uniform distribution and you have your normal distribution. Later on in the book we'll see a couple more, but really for now it's these two ways. The uniform distribution basically means that it's an interval, and that interval has the same height. Now the normal probability distribution you saw before, we've talked about this, is where our empirical rule comes in. It's mound-shaped and symmetric. 68% of the data is within 1 standard deviation of the mean, 95% within 2 standard deviations of the mean, 99.7 within 3. If it follows that approximately, we can say it's approximately normal. Remember, nothing in statistics will ever be perfectly normal. We just go off of approximations. If it's approximately, then we can use the normal model to predict some things. A couple things to note about density curves. One is the probability is never negative, so the curve should never drop below the x-axis. It should always be in that first quadrant, that positive x-axis. I guess it could sneak into the second quadrant, but it always has to be y is greater than 0. Total area under the curve is equal to 1, just like the total area of our discrete functions added up to 1, the total values of the probabilities. That's the same thing. The probability falling into any range is the area under the curve in that range. So if I'm going between 2 and 4, I just have to find the area under the curve between 2 and 4. Now don't get scared. Again, no calculus. You're either going to have to calculate it from a rectangle, or we're going to use the normal model, which is a few sections down the road from this one. The probability that x equals any single number in a continuous function is always 0. Because if you think about it, even if I'm doing an interval, and let's say we're looking at an interval from, I don't know, let's say we're looking at just a simple interval from, let's call it 2 to 5. Okay, so our interval is going to run from the number 2 to 5. If you think about it, I have an infinite number of values between 2 and 5. I could have 2, I could have 2.000001, I could have pi, I could have all these values that are between 2 and 5. That's an infinite number of values. So if I pick out one value, let's say I pick out 3.5, the probability of x being that one value has to be 0, because it's one possible value over an infinite number of values. Well, 1 divided by infinity is essentially 0. So that's why the probability that x equals a singular value is 0. For continuous distributions, the probability is going to be x is a range of values, not a singular value. If it's a singular value, that probability is always 0. Okay? Here's kind of a more formal definition for a density function. If you're really into to formal definitions, here it is for you. But basically, I'm just showing you that the probability that that my random variable falls between these two values right here on this uniform distribution, it's just this area that's highlighted in this light bluish color. The probability that it falls in the normal distribution is the same thing. It's this area and this value. Now again, this area is really easily calculated. It's a simple rectangle. Length times width, or base times height, whatever you want to call it, is calculated that way. This area we'll calculate through tables or through our calculator. You don't have to worry about that. We don't have to do any complex calculations there. A uniform distribution is just like I said. It's straight across. It's going to be uniform throughout. Okay? The uniform density function looks really complicated, but let's think about what this says. If I have a value, let's look at this again. Let's say I've got my distribution here, and this is saying that x goes from, oh, I don't know, let's do something relatively easy here. Let's say x goes from 1 to 9. So x goes from 1 to 9. So this first number here is the number 1, and the second number way over here is the number 9. Okay, let's see if I can drag this down there. All right. My uniform distribution basically just says the function with respect to x has to have the same height throughout. And if I want to find out that height, f of x, it's just equal to 1 over b minus a. So it's 1 over the larger value, 9, minus the smaller value, 1. So it's 1 over 8. So that means this height right here is 1/8. So this height right here has to be 1/8. If I do 1/8 times the width of my interval 8, I get 1. That should be the area under my curve. I've done it right. Anywhere else it's 0. So my function is just in between 1 and 9. That's a uniform distribution. So it seems complicated. It's actually quite simple. You're just finding out how wide the interval is, and then your function is 1 over the width of that interval. So here's just an example. It says Slater customers are charged for the amount of salad they take. Sampling suggests that the amount of salad is taken uniformly distributed between 5 ounces and 15 ounces. What's the probability density function? Well, first we have to look at the width of this interval. It goes from 15 to 5. 15 minus 5, that looks like 10 to me. So my density function is going to be 1 over the width of the interval between 5 and 15 and 0 elsewhere. And x is basically how much weight the plate is filled with. So that's pretty simple, right? Now we can do calculations from this as well. You know, if I want to figure out the probability that x falls within an interval here, all I have to do is find the width of the interval, multiply it by the height of this function. So if the width of my interval is 4, 4 times 1/10 is 4/10. That's the probability of it falling within a certain range of values. Okay? So what's the probability a customer will take between 12 and 15 ounces? Well, 12 ounces falls right here. 15 ounces is here. This is the area that we're looking for. So the width is 3. 3 times 1/10 is 0.3. This is really, really easy stuff. Uniform distributions are really easy. And quite frankly, they show up on your AP exam once every other year or something like that. So it's really not that big of a deal. Here's another simple example. This is just given you in function notation. Basically says the width of our interval is 8. The less than or equal to or less than does not matter, because remember, the probability of x taking on the value of 10 is essentially 0. So if I'm doing less than 10 to greater than or equal to 2, it doesn't matter. Okay? So probability x is 7. Again, the probability x takes on a singular value is 0. Probability x is, I'm going to click all these out. Probability x is less than 5. Well, the width would be from 2 to 5. Okay, so that width is 3. 3 times 8 is 3/8. You can leave that as 3/8 the fraction or 0.375. I don't care which. The width of this interval here is 2. 2 times 0.125 is 2/8 or a quarter. and the last interval has a width of 6.5. When I multiply that out, I get 0.8125. Seems quite simple, right? That's about it for uniform distributions. Your homework is on page 350, numbers 21 through 27. Good luck. Have a good weekend. And if you get time tonight, go to the high school football game. We want to see the Aves kick some Mason butt.